floor is yours.
Okay. Hi, everyone. I've said hello to most of you who came in. Yeah, this paper came out last year. Our boast, I was given the gold medal by the International Society of Multi-Criteria Decision Making. I didn't offer it to this group because it's not really on elicitation of subjective probabilities or anything like that, but it does have a lot of relevance, I guess. And Tina and Roger slightly twisted my arm, and so here I am talking about it again. I've changed a few slides and updated them, but it's basically what I said last year. And remember, it was given to the International Society of Multi-Criteria Decision Making rather than another group. But anyway, okay. It led to a paper. If you want to find the paper, it's in the European Journal of Decision Processes. It's in there, yet to be allocated, read it online early section. It's going to be a special issue from the conference, but my paper for some reason got through fast, probably because being retired, I wrote it fast. Okay, I do have an agenda. It's going to be a sort of shaping of my perspectives, gives you a feeling. It's going to be more autobiographical in many ways than anything else to start with. But then we will get through to talking about different types of decision-making models, how they relate, what might bring them together much more than you might think. And eventually I'll end up talking about some recent work we did with the IPCC just before the last climate change report. And then I might say something at the end, okay? So, you said 50 years, Tina. I became a Bayesian in 1970. No, 1971. It's my first year, my third year at university, my final year. We did a Bayesian stats course, Bayesian decision analysis course, and I was slightly hooked, and I've been hooked ever since. So it's over 50 years ago. So my early background was I did a mathematics degree. I did a lot on statistics and numerical analysis in that maths degree, and then looked around for something to do. Didn't quite know what to do, so I ended up doing Bayesian stats applied to protein crystallography. It's a great time. Got my doctoral thesis in about 1975, 76, and looked around for a job. But there were no jobs in protein crystallography, but there was a job going at Manchester in decision theory, a lecturer in decision theory. It was an interesting advert. It said no previous experience required. Well, unfortunately, all the other applicants had a lot of previous experience and were disqualified, so I got the job by default with none. And so 1976, I started off as a lecturer in decision theory, and I thought I ought to find out a little more about it and began to explore the subject. But remember, I explored it from a technical Bayesian background. I was a mathematician. I'd worked in a very scientific lab of protein crystallography with Nobel Prize winners. It was all hard science, if you like. I came into the subject from that direction, and I was very strongly Bayesian. And being Bayesian in those days, much more than today, meant all uncertainties should be modeled by probabilities. And you've got Ramsey, De Finetti, Savage, de Groot, Lindley, and I can go on, all the people who are arguing that or had argued it. They also argued that all preferences should be modeled by multi-attribute utility and value functions. So you've got Fishburne, Keeney, and Rafer in the background pushing you through that way, and so on. And then behind it all, an area of mathematics that's sort of been forgotten since this century, axiomatic measurement theory. It was about how you related the quantified models you used in mathematics to the qualitative behaviors going on in the world. And those qualitative behaviors could be descriptive, but in terms of Bayesian approaches, they were normative. They said they modeled an ideal decision maker and rational decision maker and how that person would choose. and that whole literature, Kranz, Luce, and Tversky, there's a 3-volume book by them, and there's some others, Van Zargel, Roberts, and so on, were writing around those times. And again, also in the background, we knew that behavioral studies by Kahneman, Tversky, foreshadowed by Edwards and a few other people, had begun to show that Bayesian ideals were not used in everyday life. People, when they made decisions, didn't do so in correspondence with a Bayesian ideal of rationality. They made them in lots of different ways. Obviously, because if Bayesian was the correct way, we called them biased. And we talked about heuristics and biases in a very sort of pejorative way. But we did recognize that normal human beings were not Bayesians, and therefore they had to be helped to become rational. So I came in to explore decision analysis from that direction. And I was aware that, or became very rapidly aware that there was a lot of non-Bayesian approaches to decision-making coming about. They tended to be called multi-criteria decision-making in those days. The first conferences on multi-criteria decision-making came out, I think, round about 75-ish. The dates are in the paper. I did the research and put the dates in. So there was a lot of growing methods coming up, which we'll talk about in a second. And I began to read their literature. And what did I find? Lots of things that worried me. Now, they worried me because I was a Bayesian. They weren't Bayesian, but they also worried me in a bit more fundamental way. And I became fairly critical. Firstly, almost all MCDM methods in those days were based on interactive multi-objective programming. You set up a model, a sort of mathematical program, but each step you interacted with the decision makers, got their preferences between a couple of alternatives, and that fed into the multi-objective programming model, and gradually it moved nearer the Pareto optimal frontier, or whatever you want to call it. Almost all approaches were very mathematically described. There was a huge emphasis on mathematics. Oh, whatever, it's gone, hang on. Huge emphasis on mathematics. And that's important because there was this mathematical culture throughout in our own department in Manchester, at a conference we organized, but much more generally across the whole MCDM community. And mathematics is wonderful because you've got a right and a wrong. In mathematics, there is a clear answer. Unfortunately, that's not true in the real world. And that sort of gave the MCDM community in those days, and to be fair, the Bayesian, a bias that they didn't see the world in its complex ways. There was an assumption that people knew their preferences, so you could measure them. So it wasn't like the Bayesians where we talked about elicitation and recognized that people might not know their biases, preferences. I certainly don't know my preferences, and I didn't then. I mean, you might want to think about, I don't know if you've bought an electric car yet, but if you haven't, and you've sort of got vaguely in your background, you'll be buying an electric car in the next 5-10 years. I bet you don't know which one you would buy at the moment. You need to think about, what is an electric car? I've never driven one. How does it feel? What do I want in there? What don't I want in there? I've got some ideas, but basically I've got no strong preferences. They've got to be constructed by thinking through the problem. And that wasn't recognized broadly across the MCDM community. They certainly didn't recognize behavioral issues. All the biases that I talked about a moment ago were completely unrecognized and not mentioned at all. I dared to write a paper in 1984 which said, hey folks, you ought to be looking at this. Nobody listened. Hans Dannenbach and John Buchanan wrote a similar paper in 1989. Nobody listened. Pekka Koronen and Jyrki Valenius wrote a paper in 1996 at a conference and gave it, and everybody listened and promptly forgot it. And then around about 2000, well, this century, people in a lot of MCDM communities began to really talk about biases and heuristics. To be fair, if you go back, people like AHP talked about consistency measures, but they didn't really use them in a structured way to help people think. There were no axiomatics within the literature. Bayesians had their axiomatics, but the non-Bayesians didn't. They just built mathematical models. And because you build models, you get undebated questions of rationality. So if you look at AHP, it came up with rank reversals, or it became up dependent on irrelevant alternatives, if you like. You had lots of debates in principle, but not in practice, between do you want a total order or a partial order to come out of your methods? Do you just want to know good things on a Pareto boundary, or do you want to know that what's best overall? And finally, and alarmingly to a large extent still, uncertainty was largely ignored. And if it wasn't ignored, they confused lack of knowledge and stochastic uncertainties with ambiguities. And those are things that sort of matter. But despite my criticisms and a few other people, they kept on coming up with lots of different methods. There's a few sort of acronyms and, you know, spaghetti names and God knows what coming up. And even decision analysis just came on and went on its own way. All these methods, to a large extent, developed their own communities, and they went off and did their own thing, and they didn't talk to any other. And, you know, I could add in, if the slide was bigger, I could probably put in another 20 sets of initials. And they've kept going. Nowadays, there are many vibrant, in the sense of busily working, talking to themselves, MCDM communities. They're often known, in fact, more generally known these days as multi-criteria decision analysis, but it's the same lots of amalgam of lots of different communities, not really talking to each other, just talking within themselves. And that raises a question, are all the non-Bayesian ones wrong? You know, I believe the Bayesian one's right, so do I necessarily believe all the others are rubbish? It's quite easy sometimes to believe that, but are they? I mean, there's an awful lot of intelligent people involved. If you had the good fortune that I had to meet Bernardois, who led the French multi-criteria decision aid community, that was no doubt he was one of the most intelligent people I've ever met. And, you know, both mathematically and in all breadth, he was a polymath, a really wonderful person. But was he wrong on his ideas on decision making? Why is he so much worse off, or why is he so much more likely to be wrong than Leon Savage or Jimmy Savage? So let's go back to the beginning. What's a decision? Because almost all books on decision texts start off by saying, we're going to talk about decisions, and then don't talk about what the decision is. They talk about how they're going to analyze their simple model. Well, a decision has a person who's unsure about what they're going to do. They've got a lot of uncertainties about the future, but they also have some knowledge. And that knowledge is what they want to deploy to help them face their uncertainties and make their decisions. Except most decisions we analyze aren't like that. We have most decisions involve a group of decision makers. It's not a single person, it's a group. And Bayesians ought to worry about that, because Bayesian theory only applies to a single person. So, you know, there's a group there that we have to worry about. How are we going to help them make a decision? Well, actually, it's not just one group. There are lots, because some knowledge is available in books, but other knowledge is tacit and embodied in experts. And how do we get it out of experts? How do we bring in expert knowledge? And behind this all, when you make a decision, a big decision you're analyzing, there's almost certainly stakeholders who are going to be impacted by that decision. They may be protesting about what you might do, so I've given them placards, but they're certainly active and worried about what's going to happen, and you might feel responsibilities to them. You might have legal responsibilities to them. You know, if you're working with the environmental agencies around the world, they have strong responsibilities to the communities that they serve. So how do they deal with their stakeholders? So decisions are a bit more complicated already. And then you get to things like, actually, the decision isn't often clear. There's a set of issues that you want to address, but you don't know how to deal with them. And then you've got conflicting objectives, both within yourself. Any individual person involved may not know what they want because they want it to be safer, cheaper, whatever. So it's conflicting objectives, but there's also conflicting objectives between the different decision makers and the stakeholders and so on. And there's messy uncertainties. Not all uncertainties are nice. And the experts don't necessarily agree. And the stakeholders may be antagonistic, may not even talk to each other. There may be ethical issues. What is the right thing to do? The governance situation may be totally unclear. Who has the authority to do anything and what's the legal requirements on them to do it? And where can information be fed in legally and not legally? So decision is not a well-defined concept. There's a mess there. And yet, if you look at a lot of decision books, they don't really get into that mess at the beginning. They just start off with a decision, choose between A, B, C, D, and E, and you've got some objectives and maybe some uncertainties. So maybe real decisions are too complex for simple mathematical tools alone. And I would say that many MCDM tools are fairly simplistic. And if you go back 50 years, so were the Bayesian ones. Bayesian's only has become more complex because we've got better computational methods these days. If you look at Rafer's book from 1968, Lectures in Decision Analysis, it was remarkably simple models he used, decision trees. So actually what happens when you make decisions is they're buried within a process. You have a way of bringing the discussion together and so on. And so here's a simple description of a very complex process. You start off trying to make sense of what's going on. How are you going to see what's going on in the world? What can you do? What can't you do? What are you trying to do? Trying to get hold of the whole context and model it and so on. And then when you get some models, you analyze and explore those models to see what they're telling you about the world and your preferences and so on, and what you would like to do if you were rational, perhaps, and so on. And having explored those and got a feeling for what you might want to do in a model, you have to validate it and come back and interpret it into the real world and then implement it in the real world. And as all the arrows show, this is cyclic, that's cyclic, that's cyclic. And though there's a general direction across there, you might duck back and have to do some more modeling, or duck back and do some more analysis as you go round. You might find at this point you haven't got enough information to make a decision, so you have to go all around it again. The process is multiply cyclic. And before you implement the decision, you may have to go around that a few times, and you'll certainly be doing a lot of things. Things such as, over on sense making, you're trying to set the context. You're trying to formulate the issues. You're probably trying to surface your values. And I tend to use a language now where I talk about values to be your guiding principles, what you want to do. Thou shalt not kill, if you want to go back to the commandments, but general principles. On the whole, I would rather be safe than not safe, you know, and all of these things. So you have to surface those values and then contextualize them to set your actual objectives for a particular problem you're looking at in the particular context. And you have to structure that problem. So that's all happening over here. Over here, you are doing quantitative analyses, and you're probably and ought to be doing sensitivity and robustness studies as well. And you ought to be looking at the model and seeing if it's valid in a sense. You might do that validity by doing some statistical checks, perhaps, or whatever. But you also need to do validating by looking at the world and saying, does it make sense? Is it capturing what's going on? And then once you've done all of that and you've got an idea of what to do, you want to build consensus around it. You want to do what Larry Phillips calls checking that the model is requisite. That is good enough. You now feel you've learned enough from doing that model. You're relatively confident enough to move forward and you can make your decision. And having made that decision, you need to communicate it to wider stakeholders. And also what we actually forget a lot is you ought to be documenting what you did and sending it up for audit, because certainly if you're working for a government agency, they're going to be audited in not just a financial sense, they're going to have to justify what they do to the wider public, and there'll be audit and so on. So that's a fairly complex process. And if you look at it, the only bits where you're actually using any sort of algorithmic mathematics are over here. They're the only quantitative bits. And those are the bits that most of the MCDM communities, and if I go back to the Bayesian too in the 30, 40 years ago, it's what the Bayesians were doing pretty much as well. They were simply living in the models and playing in the models, but they were ignoring all these areas. And it's probably, although these are, well, first thing is, most of this process is common to all MCDM methodologies. It's only there they disagree, and possibly even only the quantitative bits, because they all do the same sensitivity analysis, perhaps. And yet it's during the discursive, more deliberative stages of the process, all around here, that the complexities of real decision-making are addressed and got hold of, and so on. So let me move on and talk a bit more about uncertainties, because that's one area I think that a lot of MCD areas don't work in properly, even the Bayesian. And it's also nearest to what the SEJ group, these seminars on Tuesdays, get near, because we're much more concerned about uncertainties then. So, uncertainties. I've looked over my career many times at trying to categorize uncertainties. There was a paper of mine back in the 90s, which came up with 10 categories. And before that, there were other papers coming up with 7 and what have you. I've given up trying to count now. One of the last research projects I did before I retired was part of the Rhodos community, where we tried to look at all the different uncertainties that come up in a nuclear accident, and it just went on and on and on. You got lots of different ones. So I'm now only going to come up with 9, but they give you a flavor of some differences you might want to think about. The easiest one to talk about is a stochastic uncertainty or variability, aleatory, whatever you want to call it. It's things we all use probability for. We talk about randomness, everything from a toss of a coin to experimental error. Nobody seems to argue about that one, so I'm not going to. Then we have uncertainties about what people are going to do, actor uncertainties. Now, you can model actor uncertainties by random models quite easily, or simulation tools with randomness built in. But you ought to recognize that people's behavior may not be random. It may be partially unknown and unpredictable, but there's a lot of intention in there. And maybe we can model that in a rather better way. And I would argue David Rees-Insua's work with 3 or 4 other people on adversarial risk analysis now, not the greatest of title, but it's an extension of game theory, or quite a large extension of game theory, which does actually pick up behaviors in a better way. Or you can just go back to prospect theory. But there are ways of modeling behavior which might not be quite the ways that come out just probabilistically. And then as Bayesians, of course, we've got epistemological or epistemic uncertainties, lack of knowledge. What are the parameter values? Is that hypothesis reasonable? It's what all of statistics is about. So those 3 we don't normally argue about. But then we come up with some other uncertainties. Firstly, there's judgmental uncertainties. And I don't mean the judgments that we always talk about in these seminars of, is this parameter greater than this value or less than that value, and getting a 95% interval for a value and its median and so on. Those are judgments, and they're important, but there are also judgments going on in the modeling. Which model do you use? If you've worked in atmospheric dispersion, you know there are lots of different models based on different approximations to it, different assumptions about the environment and so on. If you work in economics, there's lots of different models. which model do you take? That's a judgment. And then having taken a model, how are you going to do the calculations? Are you going to approximate? Are you going to go up to a supercomputer if they're complex? Are you going to linearize? Are you going to, even in the statistical sense now, of do approximations through normal processes and things like that? So you're sort of doing regressions on regressions and all of those things. All of those involve huge judgments. Then those judgments must be subject to error. And yet I've never heard an analyst stand up and say, I'm making this judgment. Will somebody check me out for consistency and everything else? Does it make sense? And do they put into their analysis any allowance for that uncertainty? And then you've got computers are accurate, much more accurate than 50 years ago when I started working on computers, actually it's 55, we were lucky if we got 8 significant figures of accuracy. That's significant figures, not decimal places. Then about 10 years later, we used to use double precision, which means we could get 16 significant figures. Now you can go an awful lot further, but we're still using finite arithmetic. We may be using a hell of a lot of it. So there's going to be galloping inaccuracies, perhaps, unless you're doing proper numerical analysis to control those. And I hate to point it out, it is quite possible there are simple mistakes in the program. I have found plenty of mistakes in my program and equally plenty of mistakes in other people's programs that have been used for months or years, but they had an error in them. So there's computational errors. And then there's the one that people do talk about, modeling error, imperfect fit of the model to the real world. And there's been lots of discussions about that. The most famous quote, I suspect, of the last 20 or 30 years is "all models are wrong, but some models are useful" by George Box. I've heard it so many times since he sadly died a decade or so ago. But that feeling is we ought to be working on. And then there are some other uncertainties that come up when you're doing decision analysis. What do people mean? What does this concept of safety? What's public health? How do you define it for the particular context? How do you choose the attributes in a multi-attribute utility function? How do you choose the events in a belief net? All of those things. Before you start the analysis, you have some rough idea, but very often they're ambiguous and you have to sit there and discuss it and get to a better definition. Then you have to think about your values. What are the ethicals? What are the legal principles? How do they come down to defining what values you have to put into a multi-attribute utility, a value function, or whatever your MCDM method uses? And finally, at the end of it, and you've done all this analysis, is the analysis requisite for going forward to making a decision? You're going to feel some uncertainty there. How do you make that judgment? And you ought to recognize there's some uncertainty. Do we need to do more analysis, get more data, consult more experts? So there are lots of uncertainties. Those are only some types. You can argue that as a good statistician, you only want to talk about these two, but decision makers want to talk about all of them. And it doesn't help to say, no, that's not an uncertainty, that's an ambiguity. You have to work with their words and use their language and debate it with them. Okay? And if we start categorizing the groups I've clustered into 3, you've got knowledge of the external world. Those are the things that we play about with in SEJ a lot. But then you also hear these uncertainties, these things are actually modeling and analysis errors. They relate to things that we bring in by doing the analysis. We may reduce these uncertainties, but we certainly introduce further ones that need to be looked at. And down here, the internal uncertainties about ourselves. What do we mean? What do we want? So we've got scientific uncertainty. We've got we have some uncertainties that actually most analyses usually ignore and don't debate. And then we have these uncertainties down the bottom, which we can only resolve by deliberating, because I know of no probability model that will help me know whether I want to buy a electric car or a hybrid car. I need to build up those values and my utility functions and so on by thinking it through, by deliberating. So that's the background. Let's start saying something that may be a little bit more useful. Have I spoken with Cynefin to you guys before? I don't know. But Cynefin, I was introduced to around about 2002. It comes from Dave Snowden, who is militantly Welsh. There is no way of describing other than militantly. He is so pro-Welsh, it's lovely. You listen to him talking about Wales and everything else. And he wanted to talk about the context of decision-making. He didn't want to use bar, which is a Japanese word for knowledge in some areas. And he came up with the Welsh word, which is sort of the Japanese, Cynefin. And Cynefin means in Welsh a habitat. But it doesn't mean the habitat just in terms of the bushes and the grasses and the trees around you. It means, for human habitat, it means the physical environment, the cultural environment, the social environment, the historic environment, everything that goes on in the context in which you live, the environment in which you live. And roughly, Dave said, we ought to think about these environments. We can classify them very, very, very broadly. These aren't hard boundaries or whatever, into those contexts where we know pretty much what's going on. We understand cause and effect. We know if we pull this lever, that will happen, and so on. We really understand cause and effect. If we look at the mathematics you apply in models there, it's pretty much deterministic. Sorry. Then you get to what he called the knowable region. He's changed names now, but I haven't. And the knowable region is where cause and effect is pretty well understood. You understand the laws, economic laws, scientific laws, whatever, about how causes lead to certain effects, but you don't know the details. You don't know the parameters that get you there. So any analysis in this region is going to have models because you understand cause and effect, but you're going to have to work to get the parameters, which you may get by expert judgment, or you may get by statistics or whatever, or you may get by eliciting preferences. But the parameters here are going to be unknown, if you like. Then you get to the complex region where you really don't know cause and effect too well. You've got potential causes, potential effects. You've got these list of things which are probably having effects out there, the causes, but you don't quite know how they're leading to any particular cause. So if we take an event like Britain leaving the European Union a few years back, and you want to say the UK leaving the European Union, what effect did that have on economics? Yeah, at the moment, they're still arguing about it. And certainly before we left, nobody had the faintest idea. They had some potential things that would happen that could have big effects, but they didn't know how to put it together. But after the event, I'm sure in 5 years' time, 10 years' time, there will be a wealth of books about how it was the best decision in the universe for Britain to leave the EU, or how it was the worst decision in the universe, but they will be able to argue through what happened a lot more clearly, and so on. And then you have this area where he said, he called it chaos. It doesn't pop up too often, thank God. But it's where you really have got no idea what's going on. You may not even see causes and effect. You may not even see entities. You're stuffed into a context where you've just got no feeling for what is happening. I mean, it's easy to think about it if you're a primitive man or a space traveler in a science fiction movie. It's not quite so easy to think about real occasions, but one real occasion we've all lived through is the pandemic. We all knew that COVID-19, we all knew a pandemic was going to be awful, but we didn't know quite how, we didn't know what particularly COVID-19 was going to do to our economy, our health, our lifestyles, the way we live, the way we looked on government, and everything else. You can say there was only one cause there, COVID-19, but actually lots of sub-causes that went along with it. And the effects it had, when we look back to the beginning of 2020, you could predict certain causes and certain effects, but you couldn't in any way see how they were pulled together, and you couldn't see all of them. So it was really chaotic. And then gradually, as we learned, you came round. And learning is important because on Cynefin, you can talk about learning cycles. So you can see if you start off chaotic, you learn bits, you gradually begin to understand potential causes, you do experiments, you get a feeling for what the effects might be linked to each cause, you get a feeling for how strongly they're linked, you can do statistical analysis, you can get models being built that predict how different causes will lead to different effects. And eventually you can get down to an area where essentially all you don't know are the stochastic uncertainties. So you get repeatability and increasing familiarity coming around here, because at this point, you can't do any repeatable experiments. Even here, it's difficult because you can't control them. But by the time you're around here, you can repeat things. And more importantly, things have repeated themselves. You learn because things keep on happening and gradually you piece together why that happened. So we get increasing familiarity. So that means when we think about preferences, around here, because everything is repeatable and you've been familiar with it, you really begin to know your preferences because they're well rehearsed. So maybe some of the ideas of early MCDM about preferences being measurable are possible around here. Whereas over here, you're in novel situations. You don't know what's going on. You've never experienced some of the effects, so you can't have preferences. So over here, you've got to be much more about contextualizing general values to specific preferences. And any decision analysis you do in this area is almost certainly going to have to do a lot of work to construct your preferences as they are at that very uncertain time. So there's already, Cynefin is beginning to explain some of the differences between the different schools of decision making. And also over here, this will get Roger going in a minute, you've got messy problems with deep uncertainties. You have to use models, simple models, because you can't justify complex models. But they're often qualitative, and maybe you start using putative multiple scenarios to deal with them. In fact, picking up on deep uncertainties, if you look what's been happening since around 2000 in decision analysis, people have been talking more and more about deep uncertainties. It goes back to Knight, who Roger has read in 1921, though I don't think he was reading it in 1921. And Knight came up with two categories of uncertainty: strict uncertainty, where you really haven't got any probabilities, and uncertainties where you can handle probabilities and so on, science, whatever you want to call it. And the modern interpretation of that strict uncertainty is deep uncertainty occurs when there's no agreement, nor any time to reach agreement on what models to use to describe the interactions in any system you're looking at, what probabilities you might use to represent your uncertainties about key parameters, and how to value the desirability of different outcomes. Any individual involved in the decision making may have a sort of uncertainty they can get hold of, but when you look across all the individuals involved, there's enough disagreement that there's no single value, or you can get to almost anything. And that means if you have to make a decision and you try and fix some values, your sensitivity analysis will show that pretty much anything you could do might come out being optimal, or at least a lot of them will. So deep uncertainty is a big problem if you're dealing with complex matters and you've not got time to resolve them. And since 2000, there's been a community called Decision Making Under Deep Uncertainty, coming out of Rank organization and Delft University as well, looking at different types of deep uncertainty and thinking about how you might handle them. The most promising way, it seems to me, is what I call scenario-focused decision making. You start off not with one decision model in one model of the problem. You start off with several scenarios, each of which might describe the problem you're looking at, but they differ in certain fundamental ways. There may be certain events which are absolutely key, and in some scenarios you have those events happening, and in others you don't. And that gets you out of the problem of not being able to agree what the likelihood of that event is. Like, what is the likelihood of another pandemic before 2020? Roger could go off and do an SEJ analysis using the classical model and get a probability for that. And by the time he's had it, governments may well have actually had to start preparing for that potential pandemic. So there's no time to do it. But notice that gives you no attempt to span or partition the future. Maybe it does for a simple event, but in some things, it may not do. So look at the Ukrainian war. There's horrible possible consequences of the Ukrainian war, including Third World War, but it'd be really hard to come up with a partition of all futures that describe that. So you just come up with some scenarios that seem interesting, that pick up the deep uncertainties. You might, in issues where the real thing is a debate between the public about major issues, like artificial intelligence at the moment. How are you going to deal with models about whether or not you prohibit the development or slow the development or regulate the development of different forms of artificial intelligence? Maybe you need to start having scenarios that represent different value systems, from those who are fatalistic and say, oh, it's got to happen, through to the regulatory hierarchical people who say, it's going to happen, but let's regulate it and move slowly, and I'm sure we can control it, and we mustn't let it go wild, or whatever it is. So you can have scenarios that capture the worlds like that. And within each world, you build a model, and because you've taken out the deep uncertainties, you can now say, conditional on that scenario, can we elicit probabilities or whatever? We might build a different model in each scenario, but we can start analyzing. And that's been looked at by quite a few people now. I've got a paper on in JAWS, not in JAWS, in operations research about 3 years ago. But let me, for the last 5 minutes, talk about some work I finally did finally at the end of my career, paid career, with the IPCC. Before they published the last report, the IPCC was concerned that they would say, as they have said, that the world is up shit creek as far as it comes to climate issues. We need to start making some decisions. Those decisions might be made in local communities, regional communities, national communities, international communities. And that's going to mean that to do those, we're going to need analyses to structure them and so on. And we've got all these different MCDM methods, MCDA methods. How are we going to advise the world, the different communities in the world, to think about those methods? Now, the IPCC is also a UN body, and the UN generally doesn't tell people how to do things. It tells people what they should think about doing. And it might condemn them because they've done things that they shouldn't have done. But basically, it doesn't want to prescribe decision-making and governance structures. So as part of the IPCC activities, a group of us were asked to summarize all the different MCDM methods and list them by their characteristics and try and think about how they might be used in different circumstances. That slide just said what I said. So we developed this paper. There's a reference to it at the bottom. looking at all the different MCDM methods. There's only 4 authors there, of whom I'm one, but there was a heck of a lot of activity in the background behind them. And we looked at it without trying to say, in fact, by the end of it, as all of us wanted to say, I had certain effects, that the Bayesian methods were the only sensible methods of doing it. But we couldn't say that. What we did was we looked at lots of different methods. Here's a table which has lots of pages. You can look at it. This is for multi-criteria decision-making methods, which give you a full ranking and are optimal seeking. They don't just try and get you to a Pareto frontier and so on. We gave references to key publications in the area. And then for each one, we wrote a little spiel about how they faced up to different types of uncertainty: the stochastic, epistemic, and analytical, the ambiguous and value ones. We talked about the Cynefin regions, of how they would work in the known region: knowable, complex, and chaotic. We talked about the decision-making process with those 3 circles, the sense-making bits, and so on, and how they worked in there. And it's amazing how many different decision-making models have no way of actually building those models. They just leave that to sort of almost the chance of the analyst seeing a way of building the model. We talked about those different things. We also talked about the resources required, because it's no good recommending to a village in Indonesia that they use a large-scale multiprocessor computer and 2,000 different bits of data set and so on. They just won't have the way of doing it. And we also pointed to case studies of the different methods. And that paper has got all these tables, and it's set against all the discussion of all the complexities. If you remember the matchstick men at the beginning, those complexities written out in much further detail, and trying to advise the governments and other people to think that they wanted to do that. So a few final words, and I guess the words are, coming back to it and what I said back at the MCDM conference last June, July, is we are all of us who work in decision analysis sort of say we belong to such and such a school, the Bayesian, the AHPs, the European, the French school of multi-criteria decision aid, whatever they are. That's not France me, that's not French me, that's French France. Yet we sit in there and we don't talk to each other. I have one of my great successes, and nobody else would think this, at the end of my career, was persuading the Decision Analysis Society and the journal Decision Analysis to agree to take non-Bayesian papers, so long as they genuinely discussed why they were taking that route against why a Bayesian might have done it differently. So they discussed, they made constructive criticism. They didn't just go off and do their own thing. Sadly, we've had a few submissions, none of which have passed that test. They've all gone off and done that thing and not really thought about the principles that we were trying to encourage them to discuss. I believe that process and behavioral issues are far more important than they've been given credit to up to now. And so what I'm really saying is that the decision-making communities need to talk and learn from our differences a lot more. Because if we don't, some of those problems like climate change are not going to be easy to solve. We have tools that can help them. But if we don't find ways of working with other people with different tools that can also maybe help them, we're not going to help the debate. We're going to create different pockets of the debate. Thank you. And if you want to find it, that's my paper. You can find out what this was based on. The IPC stuff is there. It's in Frontiers of Climate. It's electronic. It's free. That one isn't free, but I can send it to you. And it's in the background talking a lot more about the modeling phase and so on. Thank you. So